Welcome to this session. Today we are going to discuss some of the set of operations on graphs, which in the last session we continued. Some more operations are there on graphs that we are going to discuss in this session, and walks and their classification. We are going to discuss these topics in this session. So first, composition of two graphs. Let us consider G1 and G2 are any two graphs. Then the composition of a graph is G1, G2. G1, G2. This is in this way we are going to compose. So we are going to get a graph G, and which is consisting the vertex set is V of G1 cross V of G2, and for which U1 comma V1 and U2 comma V2 are edges of this, if the following conditions are satisfied. So whenever U1 comma U2 belongs to edges of graph G1, that is U1 is adjacent to U2. The second property, if U1 is equals to U2, then V1 comma V2 belongs to Z2. That means V1 is adjacent to V2. So for this, let us consider one example. That means whenever two graphs are given, G1 and G2, then the composition we are going to take it as G1 of G2. And G2 of G1 is different and G1 of G2 is different. And whose vertex set is this? And edge set is this. So edge set we are going to consider any 2 points if I am going to consider. That means 2 points are nothing but the ordered pairs, because it is the vertex set is Cartesian product of two vertices. So whenever there is an edge, so if the following conditions are true, one is U1 is adjacent to U2, and if U1 is equal to U2, then V1 is adjacent to V2, or V1 comma V2 belongs to edges of G2. We are going to discuss one example. By taking one example, I am going to consider, let us Z1 is having a graph which is having two vertices. Let us say G1, so which is having A, B vertices. And next G2, let us take another graph which is having three vertices, X, Y, Z. So now G1 of G2 consists the vertex set as V of G1 cross V of G2, or vertex set V1 cross V2. So here V1 is, let us say, A comma B, and V2 if I am taking the vertices in other graph, let us say X, Y, Z. So the V1 cross V2, which is equals to the Cartesian product. So it is A comma X, A comma Y, A comma Z, then B comma X, B comma Y, B comma Z. These are the vertices of Z1 of Z2. So now these are the vertices. How many vertices are there? There are 6 vertices are there. Let us, I am going to consider those 6 vertices are here like this. So these are the 6 vertices. Let us, we are going to consider the first vertex is A comma X, the second vertex is A comma Y, the third vertex is A comma Z, and similarly the remaining B comma X and B comma Y and next B comma Z is the other vertex. Now see here, the first thing is U1, if there is an edge, this is the number of vertices in G1 of G2, that is 6 vertices will be there. Now if we are going to consider what are the edges of this, so for that U1 is adjacent to U2, so U1 is adjacent to V2, that means edges in G1, that is A is adjacent to B, so I am going to connect this. Then x-axis will be same and A is adjacent to B, I am going to connect this. A is adjacent to B, I am going to connect this. Then the second one is whenever A equal to B, whenever U1 is equals to U2, then we should be, there is an adjacent whenever V1 comma V2 is adjacent in the graph 2. So that is X is adjacent to Y. So we are going to connect this, X is adjacent to Y. Then the similar manner, so here I am going to consider A is adjacent to B, we have to construct, and A is adjacent to B, and A is adjacent to B. Next, YZ is also adjacent here, so connect this. Now, A, Z is same, that is nothing but U1 is equals to U2, and I am going to connect Y is adjacent to Z, so I connected that. And then the another one is, so here A is adjacent to B, A is adjacent to B, so I have to connect. Then this is whenever the edge, first vertices are same, then the X is adjacent to Y, so I am going to connect this. And next similarly Y is adjacent to Z, so I have to connect this. So this is the graph, so which is of G1 of G2. G1 of G2. Suppose if we are going to construct a graph G2 of G1, G2 of G1, then we have to consider this is a V2 cross V1. So what is the vertex set is V2 cross V1, which is equals to, suppose if you want to construct a graph of this, then the what is this V2 of X comma A, then X comma B, then Y comma A, then Y comma B, then Z comma A, Z comma B. These are the vertices in G2, V2 cross V1. Now I am going to construct a graph for this. So it is only G1 of G2. Now I am going to construct G2 of G1, G2 of Z1. So here there are vertices which are of the form, let us say X comma A, this is one vertex and this is another vertex. So X comma A, X comma B, then Y comma A, then Y comma B, then Z comma A, then Z comma B, Z comma B. So now once again the same, whenever these are the vertices of G2 of G1, then we have to construct the edges. So first one is X is equals to X is both are same, and the next V1 is adjacent to V2, A is adjacent to B, right? Then we are going to construct this. So here whenever X, Y are adjacent to each other, then we have to construct. Then this is X, Y. Next we have to construct X, U1, and here B will be there. X is adjacent to Y. Then the another one is A, B, and X is adjacent to Y. So connect this. X is not adjacent to Z, whereas Y is adjacent to Z. And the next another one is Z is adjacent to Y. Then Y is adjacent to Z. Then another one is A is adjacent to B. And the next Y is adjacent to Z. Y is adjacent to Z. So this is the graph for Z2 of Z1. G2 of Z1. So these are the composition of two graphs. Whenever if it is G1 of G2, then this is the graph, and G2 of G1, then this is the graph. Next, complement of a graph. So whenever two, let us say the given graph is Z and its complement, we are going to denote it with G dash on the same set of vertices as Z, such that there will be an edge between two vertices V comma E belongs to G dash if and only if there is no edge between V comma E in G. That means whatever the edges are there in Z, the edges will not be there in its complement. So here, let us consider I am taking one graph which is of this form. And now the complete graph, if I am considering 4 vertices, let us say 4 vertices, complete graph. Let us, I am going to construct a complete graph is like this. Because this is just similar to a universal set. Let us we're considering. Let us say A, B, C, D. This is complete graph of 4 vertices. Now, whatever the edges that we are going to, the complement, if I am going to consider, this is Z, and if you are going to consider its complement, the number of vertices will not be changed. So the number of vertices are only 4. And now edges we are going to concentrate. So A comma B, edge is not there here and it is there in the universal set. So we have to consider A to B edge. And the next A to C, edge is there. So I am not going to consider in its complement. And CD, edge is there. So I am not going to consider. AD's edge is there. I am not considering. Now BD edge is not there. So I have to consider BD edge. Then the another one is BC. BC edge will not be there. So I am considering BC edge. BC edge. That means whatever the edges are there in the original graph, the edges should not be there in the complement graph, whereas the other edges which are present in complete graph, those edges are in its complement of a graph. So totally how many edges are there? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 edges are there. So here also I am writing 1, 2, 3 and remaining 3. So there are 6 edges. So in this way we can calculate what is a complement of a graph. So now what are the properties of a complement of a graph? So here G is the set of edges in G dash. Then definitely that edge will not be there in the given graph. Any edge is there in the complement of a graph, that edge will not be there in the original graph. That is one of the properties. And union of G and its complement. We are going to get a complete graph. Suppose if I am going to say that, let us say this is a Z, this is the graph, and its complement is this. Let us, I am just taking complement, we can define it as G bar or G dash, whatever it is. Here I am defining with G dash. So whatever the vertices are there, whatever the edges are there in the complete graph, and the edges will not be there in the graph, the given graph itself, that will be there in its complement. Now we are just taking union of this. See here it is a G and this is its a complement. Then we are going to take it as Z union G complement, which is nothing but a complete graph with n vertices. So you observe this. See here I am going to construct outer graph will be the same, and inner is nothing but this star graph we are going to get. So this we are going to get the inner part, and whereas the outer part is nothing but Z, and we are going to get it is a complete graph. With 5 vertices, which is nothing but a Kurtoski's first graph. So here, this is the way that we are going to consider the union of the graph and its complement is nothing but the complete graph with 5 vertices we are getting. Then the another property is the intersection. What about the intersection of these two is null set, because there is no edge is common. So I am going to get null graph, because it is having only vertices. So here G intersection G bar. What we are going to get? We are going to get A and vertex A, and the next another one is vertex B, and another one is vertex C, and another one is vertex D, and another one is vertex E. So we are going to get a null graph. That means only vertices are there. There is no edge. So the intersection of the graph and its complement is nothing but a null graph. If G is a disconnected graph, then its complement is a connected graph. Its complement is a connected graph. Observe this. This is a disconnected graph. This is Z. Let us say this is the graph G. The graph Z. So whatever the edges will be there, those edges will not be there in its complement. Those edges will not be there in its complement. So this is the complement we are considering it as G dash or Z bar. G dash or Z bar. So this is a disconnected, whereas this is the connected. This is a connected. So this is the disconnected graph. This is a disconnected graph, whereas this is the connected graph. This is the connected one. So that is the another property. Another property. And now, so G dash is the connected graph. Order of a graph and its complement are same. Order of a graph is nothing but number of vertices in the graph as well as in its complement. As well as in its complement will remain same. Next, the size of a graph and its complement cannot be same. So what is the size is nothing but the number of edges. So here how many edges it is having? It is having only, the size of this graph is only 2, whereas this is other than the 2. 1, 2, 3, 4, 5, 6, 7. So this is order is the size is 7. The size is 7. So order is same, but the size will not be same. Order is nothing but the number of vertices in those graphs, where G as well as G bar will have the same number of vertices, but edges will not be same. So these are the some of the properties. One property is whatever the edges will be there in the original graph, the edge will not be there in its complement. And the second one is union of the graph and its complement is nothing but a complete graph. And next, the third one is the intersection of a graph and its complement is we are going to get a null graph. If a graph is a disconnected, then its complement is a connected graph. And the graph is the order of the graph and its complement are same. That means number of vertices are same in G as well as G complement. But the order will not be same. The order will be same, but the size will not be same. So order is nothing but number of vertices will be the same, but number of edges will not be the same. So these are the properties which are related to this complement. Now let us go with some problems, simple problems related to this. So we are going to consider G a graph, and E are the edges, and V denotes the vertices of the graph. So here number of edges in the original graph is 30, and its complement number of edges is 36. And what are the vertices in the original graph G? So it is given as G and next G dash. So here, so this is G dash. So here number of edges are given, it is 30, and number of edges are given 36. Now we are going to calculate what is the number of vertices in the original graph. So now if I am going to consider the edges of this edge and this edge, the union of two graphs is nothing but a complete graph. Here we discuss the union of the graph and its complement is a complete graph. So based on that, we are going to consider the number of edges. Here 30 and 36. So which is nothing but a complete graph with n vertices. Number of edges which are there in a complete graph with n vertices. How many number of vertices in a complete graph? That is nothing but 1 by 2 and n into n minus 1. So here we are going to select two vertices. In how many n from n vertices? We are going to select two vertices, because the edge can be formed by using two vertices. So how many ways that we are going to select two vertices from n vertices? N two ways. That is n factorial by n minus 2 factorial into n minus 2 factorial into 2 factorial. So this is nothing but n into n minus 1 into n minus 2 factorial by n minus 2 factorial into 2 factorial. These two get cancelled. So what we are going to get? 1 by 2 n into n minus 1. So these many edges are possible in a complete graph with n vertices. That we are going to written here. So number of edges in the original graph plus number of edges in its complement, which is nothing but the number of edges in its complement, because we are going to get it is nothing but a complement, complete graph with n vertices. Complete graph with n vertices. So we are going to equal. So subsequently we are going to simplify this. So it is nothing but 66 is equals to 1 by 2 n into n minus 1. N into n minus 1. So it is nothing but 132 is equals to n square minus n. So n square minus n minus 132 equals to 0. So that's what here. Then by just finding the factors of this, this is nothing but 12 11 jars. So it is nothing but 12n minus 11n. So it is plus n and minus 132 equals to 0. If we are going to simplify this, n minus 12 plus 11 I am going to take n minus 12, which is equals to 0. So n plus 11 and n minus 2, 12 is equals to 0. N is equals to minus 11 and 12 will be there. So minus 11 and 12, so negative number of integers, negative number of vertices will not be allowed. So we are going to consider the number of vertices, the positive integer value, that is n is equals to 12 vertices. The original graph is having 12 vertices. So like this we can calculate the how many number of vertices whenever the edges will be given in the graph as well as in its complement, how to find out the number of vertices in the original graph. Now let us go for the second problem. Consider a simple graph G, and E is the denotes the edges and V denotes the vertices of G. Let us having the number of edges are 12 and the number of vertices are given. Find the number of edges in its complement. See, the same way whatever we are discussing here, the same way number of edges in the graph plus number of edges in G dash is equals to then number of edges in its complete graph, with n vertices. And here it is given. So we are going to find out, this is given and it is 12. Then these edges we have to calculate, E of G dash we have to calculate, and the maximum number of edges are n into n minus 1. This is a half n into n minus 1. This is nothing but number of vertices. Vertices are also given. Number of vertices are 8. So 1 by 2, 8 into 8 minus 1. So after simplifying this, we are going to get number of edges are in the complement is 16. And the complement is 16. So in this way, we can find out number of vertices as well as the number of edges in the wherever the graph G or else G complement also. Now, let us go to the other topic, walks and their classification. So what is meant by a walk? So walk is a sequence of vertices and edges. Sequence of vertices and edges of a graph. If we traverse a graph, then we can get a walk. Let us say, I am going to take, this is the graph and I am going to consider, let us E1, E2 and E3, let us E4 and E5 and E6, E7. There are 7 edges and 5 vertices in the graph. Now I am going to consider one vertex 1 to E1 and next it will go to vertex 2, and next along the edge E3, then it will move to the vertex 3, and after that it will go to E4, E3, then 3, then it will become, let us E5, I'm just going E5, and it is 4, and next it will be E2, and then it will be 2, let us say, and I am going to construct 2, let us say, and next another one is E1, let us say 1, then another one is E4, and another one is 3. See here, you observe this. One is vertex, and this is the edge, this is the vertex, this is the edge, this is the vertex, this is the edge, this is the vertex, and this is the edge. Like that, it is going to be traversed from vertex 1 to vertex 3. So whenever this type of a sequence of edges and vertices, we are calling it as a walk. So here, in the walk, any number of vertices or any number of edges will be repeated. See, edges, if you goes on keeping edges in between, the walk will become lengthy. Either I can represent like this, or I can represent like this. Only vertices. In between there is an edge. See here, 1, 2, 3, 4, 5, 6, 7. 7 vertices are there. In between, only 6 edges will be there. 1, 2, 3, 4, 5, 6 edges. Either we can represent a walk in this form or else in this form. Or briefly, because to write every time the vertex and edge is tedious, so we are going to represent a walk is just vertices, and we are going to assume any 2 vertices in between there is an edge. Now, so we discussed walk is a sequence of vertices and edges, and this walk is 2 types. One is open and another one is a closed walk. So what is the open walk and what is a closed walk? So here observe this. This is the beginning of the vertex and this is the ending of the vertex. Walk, I am just considering, this is a walk. In this, 1 is the beginning vertex and 3 is the ending vertex of a walk. So both vertices are not same. So we can say that both vertices are different. We can say that that is open walk. Whenever these 2 end vertices will be the same, I am going to consider, let us say 1, E1, 2, E3, then 3, E4, 1. You observe this? Beginning vertex and ending vertex will be the same. In that case, we are saying that this walk is a closed. See here, whatever we discussed in the example, the same thing is a open walk. Whereas we are going to discuss, see here, open, beginning vertex and ending vertex will not be same. And a closed walk is beginning vertex, ending vertex will be the same. Then we are saying it is a closed walk. Now, trial. What is meant by a trial? A trial is an open walk. See here, open walk. In this, will be a trial. Trial is an open walk in which no edge is repeated. Vertices are allowed to repeat. See here, 1, 2 in this diagram. Let us say 1, 3, next 8, 1, 3, next 8, next another one is 6, next another one is 3, next another one is 2, next another one is 2. Next, if I am going to consider like this, so if I am going to consider like this, So this is beginning vertex is not equals to ending vertex. So it is open walk. It is a open walk. Edges are not repeated. This is once traversed. This is another traverse. Next this. Next this is. Next this is. All vertices, all edges are traversed only once. But vertex 3 is repeated. Vertex 3 is repeated. So we are calling this as a trial. This as a trial. Suppose if I am going to consider, let us I am going to consider this path alone. So like this also we have to consider. Suppose 1 to 3, 3 to, this is 1 to 3, 3 to 8, 8 to 6, 6 to 3, 6 to 3 to 2, 2 to 1, 2 to 1. So here this is a closed walk. This is a closed walk in which no edge is repeated, but vertex is repeated twice. Vertex is repeated, 3 is repeated twice. So it is known as a closed trial. Closed trial. So trial is, we can say it is an open walk. Trial is an open walk in which no edge is repeated, but vertex is repeated. So these are the examples for a trial and the closed trial. Now next another definition is circuit. What is a circuit? So circuit is traversing a graph such that not an edge is repeated, but vertex can be repeated and it is closed also. So that is, it is a closed trial. If I am going to consider a closed trial, it is known as a circuit. A closed trial, which is known as a circuit. So here vertex is repeated, but edge is not repeated. Let us consider the example. So 1 to 2. See, observe this. 1 to 2, 2 to 4, 4 to 3, 3 to 8, 8 to 6, and 6 to 3, 1. You observe this. The green edges. So it will move 1 to 2, 2 to 4, 2 to 4 to 3, then 3 to 8, 8 to 6, 6 to 3, 3 to 1. That means the 3 is repeated twice. 3 is repeated twice, but the edges are not repeated. Edges are not repeated. So it is a circuit. It is a circuit. Circuit is nothing but a closed trial. Closed trial. So now let us consider a path. What is a path? If it is a trial in which neither vertex nor edge are repeated. Any trial. Trial is what we are saying that any vertex is allowed to repeat, but edge should not be allowed to repeat. So such is known as that is known as a trial. So we are going to consider a trial in which vertex is not repeated and edge is not repeated. Such a trial is known as a path. Such a trial is known as a path. Let us consider this example. So here 1 to 2, 2 to 4. Let us I'm just considering 6 from 6. 6 to 8, 8 to 3, then 3 to 1, 1 to 2, 2 to 4. Once again, 6 to 8 and 8 to 2, 8 to 3, then here you observe this. Here, no vertex is repeated, no edge is repeated. So this is, we are calling it as a path. We are calling it as a path. 6, 8, next 5, next 1, next 2, next 4. So this is the path. Now what is a cycle? What is a cycle? Traversing a graph such that we do not repeat a vertex, or we can repeat the edge, but starting and ending vertex must be same. Then that is, we can repeat the starting and ending vertex, then we get a cycle. So here also, starting vertex is equal to the ending vertex, but the remaining vertices will not be same. So it will be different. So here let us say 1 to 2, 2 to 4, 4 to 3. This is one cycle. Suppose if I am going to consider like this. This is another cycle. This is another cycle. So if I am considering this is another cycle. This is another cycle, like this. So if I am considering this is another cycle, like this. So in the cycle, the beginning vertex is equals to ending vertex, and inside other vertices and edges are not repeated anywhere. So cycle is a closed path. Cycle is a closed path. Now, we are going to concise all these things in one diagram. So, walk-in graph theory. So, walk-in graph theory means is a sequence of vertices and edges is known as a walk. So, here we are going to say that vertices walk is a closed walk and open walk. See, in the walk, if neither edge nor vertex is repeated, that means vertex and edge, if it is not repeated, then that is known as a path. Edge is not repeated, but vertex is repeated, then it is a trial. So every path is a trial. But every trial need not be a path. Every path is a trial, but converse will not be true. And suppose the path is closed. That means neither edge nor vertex is repeated. Of course, the beginning and ending vertex is repeated. So that is known as a cycle. And here, trial, no edge is repeated, but is a closed one. If it is a closed walk, no edge is repeated, vertices are repeated, then that is known as a circuit. Now, every cycle is a circuit. But converse need not be true. Any circuit may not be cycle. So cycle may be circuit. Every path is a trial, but trial need not be a path. Every cycle is a circuit, but circuit need not be a cycle. So, these are some of the examples based on the walks and their classification. Suppose we are going to consider a graph is like this. Now, see here there are given V1, V2, V3, V2. V1, V2, V3 and next V2. Let us V1, V2, V3, V3 and next once again V2. So this is V1 and next this is V3 and once again it is going back. So it is nothing but a open walk. Edge is E2 edge is repeated twice. But it is a beginning vertex and need not be a ending vertex. So it is a open walk. And now see here V4 to V5. Then the number of edges, if I am going to consider E7, E1, E2 and next E3 and next E4. See all the edges are different and all the vertices in between are different. All the edges are different and of course vertex V4 is repeated and other vertex is not repeated. So it is nothing but it is an open walk. So and vertices are repeated, so it will become a trial. Next here V1 and V5 are different, so it is an open walk in which see here E1, E2, E3, E4. That means all edges are distinct. All edges are not repeated any edge and vertices are not repeated. So this is an open walk in which vertices and edges are not repeated. So it is nothing but a path. So here once again V1 to V1, this is a closed walk in which then let us say E1 and E2, then E3 and next E7. All edges are different. Then V2, V3, V4. All vertices are also different. So it is a closed walk in which vertices and edges are different. So it is nothing but a cycle. Of course, beginning and ending vertex is same. Then Once again, we are going to consider V6, V6. It is a closed walk in which see E5, E4, then E3, then it is E2, E1, E7, and E6. Of course, all edges are different, and whereas V5, V4, V3, V2, V1, and V4, and see here V4 is repeated. V4 is repeated. V4 is repeated. So it is a closed walk in which vertices are repeated, but edge is not repeated. So it is nothing but a circuit. It is nothing but a circuit. So like this, we can classify whatever the walk will be there. The classification of the walks by taking one example, and we are going to give a conclusion. What type of walk it is, either it is an open walk or closed walk or cycle or a circuit. So with this, I'm going to conclude this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.